This is Professor Stugard, and in this video we're going to be discussing correlation. So in this video we're going to talk about a few things. First, we're going to review what correlation means in terms of statistics, and again, you might actually remember this from your statistics courses already. And then, of course, what our correlation coefficient is. Then we're going to talk about how we can calculate our correlation coefficient in the programming language R. And then we're also going to talk about how we can plot what are called correlation coefficient matrices, which are an important part of doing some exploratory data analysis. So first of all, let's make sure we know what a correlation really is. So when we're looking at our variables, if we want to see if there's a correlation or an association between two of our variables, we really want to see if there is a connection. And typically we think about it in terms of a response variable, which is related to our explanatory or our predictor variable. So our explanatory variable gets plotted on the horizontal axis, and we treat it as our independent variable. And then our response variable then gets plotted on our vertical axis, or we treat it as our dependent variable. And so again, those are really just names. We don't necessarily say that one is a response to the other. We don't necessarily know what kind of relationship exists, but that is the terminology that we use. Another important thing to recognize is that when we talk about correlations, we're going to be focused on the correlation coefficient, and we're also going to want to visualize whether there's patterns in our scatter plots, which means our data must be quantitative. So if I'm looking at scatter plots, it must be quantitative here, meaning that it must be numerical. We can't do this with our categorical data or qualitative data. We have to be dealing with numbers here. So the types of patterns that we're going to be looking for are linear patterns. And so in that first graph, if I have a scatter plot, right, if I plot my two variables with my explanatory and my response, if it appears like they are going in an upward trend in a line, we say that that is a positive association, right, kind of like that arrow. And then similarly, if my ordered pairs seem to be following a pattern of a line, but in this case it is decreasing, we call that a negative association. And those are the two types of linear correlations that we're going to be able to investigate. So how do I do that in the programming language R? Well, again, looking at a scatter plot isn't necessarily good enough. What we want to actually take a look at is what's called our sample linear correlation coefficient, or I'm just going to call it the correlation coefficient for short. Typically that is represented by the variable r. You may see in some places that they use the Greek letter for r, which is rho, which looks more like a p, but again, we don't have to necessarily worry about that in our case. So we want to calculate our correlation coefficient r, and in the programming language R, we use the function cor, C-O-R. And our arguments are going to be two numerical vectors. And again, like I said, it has to be quantitative data. We cannot use categorical data. So again, we need two vectors that are stored as numerics. Again, the nice part about this correlation function is as well is that in our data frame, typically we store our columns are all stored as vectors. All right, so we do have some properties of our correlation coefficient. First of all, our correlation coefficient is always going to be between -1 and 1. Those are the bounds for it. And the closer we are to +1, the stronger evidence exists of a positive correlation between those two variables, or right, that kind of upward slope. The closer we are to -1 is the stronger evidence that we have a negative correlation between those two variables. So again, +1 and -1, those are the extremes of my correlation coefficient, and the closer we are to either extreme, the more evidence we have for that relationship. What that also means is that the closer we are to 0, the less evidence we have for any sort of linear correlation between these two variables. So one thing to keep in mind too, the nice part about the linear correlation coefficient, it's unitless. It's a unitless measure of association, which means it does not matter what units my variables are stored in numerically, and it doesn't matter what the values are either, how big or how small they are. As long as they are numerical, we can calculate this correlation coefficient. However, we also do want to recognize that the correlation coefficient is not resistant. So what that means is it's going to be affected by outliers in our data. So if we have any extreme data values, it will absolutely kind of skew and affect our correlation coefficient when we calculate it. So, like I said, if we're close to 0, it means there's no linear association, but that does not mean that there's no association whatsoever. It could be that our data follows a different pattern that's not a line. And so we can see here in graph C and D that clearly our points on our scatter plot are forming some sort of pattern, but that pattern is not a straight line. And so my correlation coefficient is going to be close to 0, just as if there was no correlation. If all my points on my scatter plot were randomly kind of all over the place and there's no pattern, well, the correlation coefficient does not recognize a pattern that's not a line from no pattern whatsoever. So this is really something where, again, we want to work with our correlation coefficient and the scatter plot together. One of them by themselves really is not going to be sufficient for what we want to do. So the most important part about this entire fact is just because we do show that there's a correlation, so we calculate our correlation coefficient as close to 1, we plot our scatter plot, and we can see that there's a pattern there, it is really critically important to remember that that does not mean that necessarily one caused the other. All right, in statistics and in data science, we can never, ever, ever claim causation. Now, again, that doesn't stop journalists and the media from claiming that there's causation. But again, typically in statistics and data science, we cannot claim that there's any causation because sometimes we don't know, does one cause the other? Is there some sort of feedback loop? Or could there be some other factor that's affecting both of them? And typically we really don't know. We're just looking for patterns in the data and we're trying to communicate any patterns that we find. We're not making any claims about cause and effect here. So again, be really careful with that. And of course, also, anytime you're reading a news brief and someone claims that something causes another thing, well, definitely take that with a grain of salt because the media has been known to exaggerate to make more money from advertising. So we can't claim causation, and be careful of any time that you see someone that does claim causation. So the correlation coefficient is an important part of our exploratory data analysis, or EDA, and sometimes one of the good places to kind of start with our EDA is to determine the correlation coefficient between all of our quantitative variables, right? Every numerical variable, let's see what our correlation coefficient is, and again, that'll give us a really good idea of where to start with looking for patterns in our data. Now, the really nice part is we can actually use that correlation function on an entire data frame, but only if every single column or variable is stored as a numeric value. Then we can actually pipe our entire data frame into the correlation function, and it will tell us the correlation coefficient between every single one of our variables in a matrix. So let's take a look. So for example, let's say I have a data frame that has the top 100 restaurants in terms of sales. So my data frame is stored as top 100 sales. It is a tibble that is 100 by 6, so 100 observations, right, the top 100. And we have 6 variables. So my variables are the restaurant, which would be the restaurant name. We see McDonald's there at the top. The sales, the year-on-year sales, which is the increase in sales as a percentage. The number of locations for each restaurant, the YOY locations, which is, again, the year-on-year increase in locations. And then lastly, the sales per location. So again, I want to see, given this set of data, are there any patterns between my numerical values? But we have an issue. The name of the restaurant, that's stored as characters. That's not a numerical value, which means I'm going to have to get rid of that column if I want to find my correlation coefficient matrix. So, well, that's exactly what we're going to do. We have to remove that column first. So we start with our top 100 sales. We're going to pipe that in. And to remove a variable, to remove a column, we use our select function. So I'm going to select to remove or minus restaurants from that data set. So again, that's going to give me my data set with the restaurants taken out. Then everything else will be numerical. So since it's all numerical, I can now pipe it into my correlation function. And when I run my code now, I'm going to get as an output, well, this matrix. And we can see that my variables are along the vertical and along the top. And what we're looking at, each entry is well, a number between -1 and 1, and it's going to be that correlation coefficient between those two variables. And so, again, we can see, if we look at sales, all right, well, how related is it to the other variables? So a one-to-one correspondence with sales. So sales has a one-to-one correspondence with sales, which should make perfect sense. It's the same variable. Of course, it's going to have a perfect one-to-one relationship with itself. And you can see along the diagonal there that, well, anytime a variable is correlated with itself, it's going to have that perfect one-to-one correspondence. So my diagonal is always going to be just a bunch of values of 1. And the rest are now these numbers. But, well, this is accurate, and it is useful. It's not as useful as it possibly could be, because looking at a giant table of numbers is not always the best way to go about things. We want to visualize things. We're visual people. That's one of the benefits of using R, right? Is that we can create our visualizations. And luckily, we have a package that can do this. So we can create a visualization of our correlation coefficient matrix if we load the package CorePlot. Now, CorePlot is not part of Tidyverse, so you do have to load this one separately. So you're going to have to install CorePlot and then run it as library CorePlot, and then we'll be able to use the function, well, CorePlot. But we do have to make sure that we actually install and load that package first. So what this is going to look like now is we basically take what we did before. Top 100 sales, remove that column for restaurants, pipe it into the correlation function, and then that correlation coefficient matrix, we're going to pipe into the CorePlot function. And when I do that, it's going to create a plot, right, in my bottom right corner where I get my, well, plots. And now it took all those numbers and converted those numbers to circles. All right, and the bigger the circle, the closer we are to the 1 or -1. And then the darker the blue, the closer we are to a perfect one-to-one correspondence for a positive association. And the darker red we are, the darker red would tell us how close we are to a perfect negative association, right? Or that kind of decrease. And so now I can visualize, I can see very quickly, well, what's my biggest correlation coefficient, and then I can examine whether or not there's a relationship between that data. So it looks like the biggest circle in the darkest blue is, well, that one. Now, that same circle actually exists on both sides of that diagonal because, well, it's going to be the same. You're going to be symmetrical about that line down the middle because, well, it doesn't matter which one's the explanatory, which one's the response. The formula doesn't care. It's just going to do the math on it no matter what. So in this case, that looks like the darkest blue. So my next step would be to take a look at those two variables, which in this case are the year-on-year sales and the year-on-year increase in locations, and graph it as a scatter plot to just make sure that that relationship actually does exist. And again, this one should kind of fit, right? This is making some sense, right? If I have an increase in sales, I probably also have an increase in locations. So yeah, right? As I make more money, I'm going to open more locations. Or once I have more locations, I'm going to have more money, assuming I'm running a successful restaurant. So yeah, that kind of makes sense that those two should be correlated together. Now, I'm going to graph a scatter plot, and I'm going to pick one to be my explanatory and one to be my response. But again, hopefully we can see that it might not be as clear-cut as one causing another. That's why we can never claim causation. Because in this case, it probably is a feedback loop. You make more money, you open more restaurants. You have more restaurants, you make more money. And again, assuming you're all successful. So I'm going to create my scatter plot. I'm going to take my top 100 sales, pipe it into my ggplot function, my aesthetics, my x-axis. So my x-axis is going to be the YOY sales. My y-axis, my vertical will be my YOY locations. And a scatter plot means I'm going to use geo and point. And when I run that, well, there we go. There's my scatter plot. And sure enough, look at that. All my points seem to be lined pretty much in a straight line going up. And so now, again, I can create a story about this data. I know that there's a relationship. I see the relationship. I know algebraically there's a relationship. I know visually there's a relationship here. And I can build on it now and create my story about how an increase in sales and an increase in locations are going to be related to each other. All right, so to wrap this one up, can we answer the following questions? Question number 1, if a correlation coefficient is really close to 0, does that mean there is no relationship between the variables at all? So yeah, if it's really close to 0, there's no linear correlation, right? The linear Correlation coefficient only tells you if there is a pattern in a straight line. So if it's 0, does that mean there's no relationship at all? Or is it just no linear relationship? Number 2, what package do we need to create our correlation coefficient matrices? So it's the one package we talked about. That package, that function, what is it? And number 3, if we suspect there is a relationship between variables, what else should we do? Is it enough to have just the correlation coefficient? No. What else do we need to do? All right. Well, I hope this has been helpful. And as always, take care of yourselves.